So hello everyone, this is lecture 33 for the lecture in magnetism. In the last lecture we were discussing about the reflection and the transmission. We have discussed the cases where the incident wave was normal to the incidence, and there we discussed the two cases when the electric field was in the plane of incidence and perpendicular to the plane of incidence. So we have discussed those two cases in the normal incidence. Now this time we will see that if incident wave is obliquely incident on the interface, then what happens? Means how the electric field magnitude or the amplitude will change. So you'll see the relation. So see, it is incident on the theta I angle, so we call it as angle of incidence, and this is angle of reflection, and this is angle of transmission, and this is the normal to the interface, the z-axis. Now this time also the plane of incidence is this xz plane, and the plane of interface is nothing but this xy plane. So interface is nothing but xy plane, and the plane of incidence is xz plane. And now see, this theta I will always be equal to theta r, and this is nothing but law of reflection, and this is because of this. And this sine theta t over sine theta I will be equal to n1 over n2, where this is the refractive index, and this is nothing but Snell's law, so law of refraction we call it. So it is sine theta t by sine theta I equal to n1 by n2. So must remember these two laws, so we will use them. Now see, again at the interface we will see that free charge density is 0, and free current charge density means free current density is also 0. And now I will directly write the results, but before that let's see what will be the boundary conditions here valid. So see here, this electric field is in some angle, means it is not parallel to the interface. So we'll see that there will be a parallel component and there will be a perpendicular component. So this first condition will be satisfied because there is parallel component, so we'll use this. And this perpendicular component is also there, so we'll use this also. And b1 will be in the direction, so that E cross B will become K. So B is in the parallel to the interface, so there will be no perpendicular component of B, but there is parallel component of B to the interface. So this equation is also will be used, but this equation won't be used. So using these three equations, we will just do the same derivation, but we don't need here because from the exam point of view you only need the result. So EOR, reflection, will be came out to be E naught I alpha minus beta alpha plus beta. So reflection amplitude will be changed according to this, and where this alpha and beta are nothing but alpha is equal to cos theta t by cos theta I. So cos theta t over cos theta I will give you alpha, and beta is, as you already know, mu1 v1 divided by mu2 v2, and in the non-magnetic material mu1 mu2 are nothing but mu naught, so it will be equal to v1 by v2, which is equal to n2 over n1, where this n2 and n1 are refractive indexes. So this will be your result, you must remember them. So reflection amplitude will be changed like this compared to incident amplitude, and transmission amplitude will be changed according to this compared to incident amplitude. Now see here, if this alpha is greater than beta, then the reflection amplitude and the incident electric field both will be in the phase. But when alpha is less than beta, this will be negative, means the reflection and the incidence electric field will be in out of phase. And when this alpha becomes beta, then this reflection coefficient will become 0, because this came out to be 0, means when this alpha becomes beta, then there will be no electric field in the reflection component, there will be no component in this side. So that angle at which the reflection coefficient or the reflection amplitude becomes 0 is called a Brewster's angle. So this will be positive when alpha greater than beta, negative when alpha is less than beta, and 0 when alpha equal to beta. And when this condition satisfied, then the incidence angle is called the Brewster's angle, theta b. So we will see the condition. Means let's see if theta I equal to theta b means Brewster's angle and alpha equal to beta, and let's find this angle. What is this angle at which there will be no reflection amplitude? So let's find that. So what we will do, we will just put alpha equal to beta, and we will find the relation to find the theta b. So let's just equate them. So theta I equal to theta b, that is some Brewster's angle. We just compare incidence angle with the Brewster's angle. And at alpha equal to beta, that means cos theta t equal to cos divided by cos theta I equal to n2 over n1. From here, this equal to this. And now the cos theta is nothing but under root 1 minus sine square theta t, and sine square theta t can be find it from here. Sine theta t equal to n1 by n2 multiplied by sine theta I. So sine square theta t will be square of that. So it will be 1 upon this square divided by cos theta I can be written as 1 minus sine square theta b, because this is nothing but cos square theta b, and cos theta b equal to means theta b equal to theta I. So this is again cos theta I. So you can write this in this way, and this is equal to n2 over n1. Now square both sides, you will get this. So this is just a simple calculation now. So from here this will be equal to n1 square will go this side, and just multiply inside. and take this side common, take sin square theta b common, then it will be n2 square by n1 square minus 1. Now this is nothing but take the LCM, it will give you n2 4 minus n1 4, that will be n2 square plus a square plus b square, a square minus b square. So that will be this. Now this will cancel out, and n1 square will cancel out, you will get sin square theta b, sin theta b equal to n2 by n plus n2, n1 square plus n2 square under root. So this you can see it is very easy. Now from here theta b is nothing but sin inverse n2 over n1 square plus n2 square under root. So in the more easy way you can write, because this is nothing but you can just use the Pythagoras theorem here. So this is a right triangle. So where this n2 is nothing but perpendicular and this is your hypotenuse, then this will be your the base will be n1. Now from here tan theta b equal to n2 by n1. So theta b can be written in the tan inverse also, that is n2 by n1. So Brewster's angle is n2 by n1 and the tan inverse of that. So whenever you have something like this situation and you need to find that at which angle that this reflection coefficient or reflection component of the electric field will be 0. So the theta I should be equal to theta b, and that angle is nothing but tan inverse n2 over n1. So if ray is going from this medium to this medium, then n2 over n1 and tan inverse will give you the angle, the Brewster's angle. And when you are going from the n2 medium to n1 medium, then that will be equal to tan inverse n1 by n2. So that's how you can find the Brewster's angle. So 1 to 2 it will be tan inverse n2 by n1, and for the 2 to 1 it will be tan inverse n by n2. So that is your Brewster's angle. So I hope it is clear to you. Now let's find the reflection and the transmission coefficients. So again here the wave is incident obliquely, so the intensity is measured always perpendicular to the interface. So we need to see the perpendicular component. So this is perpendicular component, nothing but intensity, and dot product with the z cap will give you the normal incidence, and here also you need to dot product with the z cap, that will give you normal outward intensity. So reflecting coefficient nothing but intensity, reflected intensity, and divided by the incident intensity. So that is dot z cap and dot z cap. So we just take the perpendicular components. So again this will give you cos theta and this will give you cos theta I, and the remaining thing will remain same, epsilon 1 v1 a naught square r, and this. Now this will cancel out because these are equal. Now E naught r divided by E naught I, can we find it from here? From this E naught r divided by E naught I is nothing but alpha minus beta divided by alpha plus beta. So square will give you square of this. So this is equal to square of this. So this is your reflection coefficients. Now transmission coefficients is again means you need to take the perpendicular component to the interface. So dot z cap, dot z cap. So this transmission will give you epsilon 2 v2 cos theta 2 E naught t square, and here epsilon 1 v1 cos theta I E naught I square. So from here, so this E naught t divided by E naught I you can find from here, E naught t divided by E naught I, and the square will give you 4 over alpha plus beta square. So this will be give you 4 alpha divided by alpha plus beta square. Now n2 will cancel out n2, and this epsilon 2 is nothing but epsilon naught n2 square. I already explained this how it is. So now this n2 over n1 will give you beta, so it will be 4 alpha beta divided by alpha plus beta square. So this is your transmission coefficients, and r plus t will always be equal to 1. So this is the case. Now this is your first case when the electric field is in the plane of incidence. Now let's say the electric field is in the perpendicular to the plane of incidence. Then this is your case second. Now this is your perpendicular component electric field, then B will be in the plane of incidence. Then how things will be changed. So I will write the direct results, and here let's see what will be the boundary conditions. So see, there will be electric field in the perpendicular to the incidence, so that will always remain parallel to the interface. So there will be no perpendicular component of E, but there will be perpendicular component of B and a parallel component of B also. So what this time the conditions will be satisfied, only these three. Means there will be parallel and this and this. So there will be no perpendicular component of B, but of B and B you will have the parallel in the perpendicular, and the E also the parallel one. So there will be no perpendicular component of E when the electric field is perpendicular to the plane of incidence. So that is the case. Now the boundary conditions are different, then there will be different results for the amplitude of the electric field, for the reflection and the transmission. So these are your results you will get. So you don't need the derivation from the exam point of view. So reflection will give you 1 minus alpha beta 1 plus alpha beta incidence, and transmission will be 2 upon 1 plus alpha beta incidence. Now these relations you must remember, and again we can say that this is positive when alpha plus beta is less than 1, and this will be negative when alpha plus beta is greater than 1, and this will be 0 when alpha beta equal to 1. And when this will be 0, then reflection coefficient will be equal to 0, means this is equal to 0. So let's find, means this will be 0 only when their angle is Brewster's angle. So we can find the Brewster's angles also. So let's find the Brewster's angle. So alpha beta equal to 1. From here alpha will be 1 upon beta. And now this alpha, again we can just write the relation, this equal to this. So we'll solve that in the same way as we did in the last. So now this time we will get some contradictory result, that is n1 equal to n2. And now see that we assume that n1 and n2 are different, but in the result we are getting n1 equal to n2. So this is a contradictory result which says that there will be no Brewster's angle when the electric field is perpendicular to the plane of incidence. So theta b is not possible in the non-magnetic material. So this is the ideal case when there is non-magnetic material. Only then we will say that there is no Brewster's angle possible, because this can't be true. Now let's see the reflection and the transmission coefficients here, and see that transmission and the incidence will always remain in phase, because this will be positive. Now again reflection will be give you intensity in the z cap direction, and the incidence and the reflection intensity in the z cap direction. So it will be 1 minus alpha plus alpha beta square, 1 plus alpha beta square. So you can just find them from here. This will give you direct result as we did here. So this is the same thing. So this is your reflection coefficient, and the transmission coefficient will be 4 alpha beta divided by 1 plus alpha beta whole square. And the r plus t will always remain equal to 1. So this is your second case. So must remember these results, these two, and this r and t and these conditions. And here also the r and t values, and how this er and et related with the incident amplitude, and what boundary conditions we apply, and what is the Brewster's angle. So you must remember these conditions. Now let's see the unpolarized light and how it is polarized. So let's say this is your interface. This is your interface, and light wave is coming like this, EM wave is coming like this and going inside the medium. So this is your incident, this is your reflected wave, and this is your transmitted wave. So theta I will be equal to theta r always. Now we have assumed that the light is polarized, means electric field will be in the only in two direction, that is perpendicular and the in the plane of incidence. So there will be two direction only. So what happened to this? So we have considered only two component of the electric field, that is perpendicular to the plane of incidence and in the plane of the incidence. So we call that as superposition of two linearly polarized light, because it is polarized only in the two directions. That's why it is two linearly polarized lights and the superposition of them. Now we will study in detail that how the superposition works. But here just remember that if you have the two linearly polarized and they have the same amplitude, then that will give you a circularly polarized light. So that is your circularly unpolarized. Now it is something like Ex component, the Ey component, that is E naught cos kz minus omega t and E naught cos kz minus omega t. So we have assumed these two components, and that will give you square, will give you E naught square. So this is something like this. That's why we call that as circularly polarized. Now when it is fall on this, then there will be some reflection, and after that this component will change and this component will change according to the relation we just find. The amplitude we have find it already. So that will change, means some amplitude will be larger and some will become very smaller. And also in the transmission, the amplitude will be bigger or the smaller. So that will be changed according to the relation we just find here. So according to them, they will change. Now see, we'll call that as partially polarized, because there will be both are available, and here also both are available. So we call them partially polarized. And now see that amplitude will be different. Here the amplitude was same, so we call that as circularly polarized. But here the both amplitude will be different, the perpendicular and the parallel. So that's why that will give you the superposition of that will give you elliptical polarization. So we'll see in detail how what is elliptical and what is circular. So just remember that if amplitude are different, you will get elliptical polarized light, and here also, and we call that as partially polarized. Now what happen if theta I become the Brewster's angle, means the incidence angle is nothing but tan inverse n2 over n1. Then at that angle, what happened that this component, the perpendicular component to the incidence, will become, means only this component which is in the plane of incidence, that will be removed, because we studied here that there will be no component of the reflection when the Brewster's angle come in the picture. So see, at the Brewster's angle alpha will become equal to beta, and this will be 0, means there will be no component in the reflection plane. So there will be no reflection amplitude of the electric field. So this will become 0, and here the electric field is in the plane of incidence. So there will be, again as we are seeing here, so what is the component in the plane of incidence? That is this one. So this will be removed here. If it is incident on the Brewster's angle, then this component will be removed, only this one will remaining, the perpendicular to the incidence. So if this is your unpolarized light, then at the theta b, only this component will be remaining, and the other one will be removed, and we'll call it as the completely polarized because there was only two component and one is removed, so only one is remaining. So we'll call it as completely polarized, and the direction of polarization is perpendicular to the plane of incidence because only this component will be remaining, because it was not becoming zero here when this electric field was perpendicular to the plane of incidence. So only this component will be removed, and here this component will never become zero. I mean there will be both component will be there always, and that's why this will always remain partially polarized. But this can be done as completely polarized when there is only two components. But in the ideal case this become true, but there are all the means component in all the direction. So here we just consider the ideal case when there is only two linearly polarized, and which is perpendicular in the parallel. So in that case you will get only the one component that is perpendicular to the plane of incidence, and you will get the completely polarized light. So this is also a possible condition, you can make that. So we'll see in the next lecture that how the superposition works, and we will see them in detail. So that's it for today. Thank you everyone.